oh, that's port 7 HTTP, oh, that's port 80 or something. And we want to say, in the little example we just showed, it was a 100-byte thing, but we want to say how much information is being sent, the actual payload, not counting this crux that we're adding on to. And then we have to have similar things as to where it's coming, where this thing came from, because when it does get to the other end here, we generally have to resend a reply back. So there'll be the internet number of your home machine or wherever it is you're running your SSH program from. And it won't be port 22. This is the port on which the SSH daemon listens to. But when you fire off SSH at home, you're not running the daemon there, you're running just that user program. It picks some unused, high-numbered port to work with. And we give the other machine that port. So when Rohan eventually responds, it's going to send things not to port 22 on your local machine, but on whatever this port number you told it to work with. Okay, so another little aside here. This is sort of like the telephone operator, at the front desk of a building or whatever. You go up to the front desk and you say, I want to see Mr. So-and-so or whatever. You don't continue talking to this person at the desk. He sort of shunts you off to some other place. Take that elevator and go up to that apartment. So the same thing happens with the SSH daemon. It gets the initial call here, but when it sends things back, it's going to give directions. Hey, from now on, don't talk to me. Talk to port number or whatever it was. It's going to pick some other big port number, free one on Rohan. And then you have a conversation between those two ports, which no longer have anything to do with 22. You keep port 22 open for new incoming connections and move each individual conversation then off to different pairs of ports. Okay. All right, so that's some of the stuff that you'll find in the packet there. So the where to send the replies to, what port to send the replies to, and there's also things like sequence numbers in there. And so that as we get these packets showing up on the other side, we can figure out which one goes first, which one goes second. And we also can acknowledge or negatively acknowledge the data itself. If it turns out that the error correction code that we wind up putting on at the very end here, at this layer here, doesn't check out, then this protocol is going to be responsible for asking for that information again. All right, but one of the things TCP is not responsible for is figuring out how to get this packet to Rohan. All it's got is this internet address, and it sticks that in its header file, and now it's no longer its headache anymore. It's going to pass this down to the next lowest layer. That's the IP layer, the network layer, and the internet protocol takes over. All right. So IP probably also does not have a clue as to how it's supposed to get to 131.91.3.100. But that's not its main job. Basically, it's not going to tell you how to get to the destination, but how to get one step closer to the destination. We've seen even across town, you might have to go through 20 hops. So we're just trying to figure out what's the next hop. How do we do that? Figure that out, it's going to look at its routing tables. Last time we looked a little bit like Legolas's routing tables. And they said things like, hey, if the address you want is 10 dot something or other, fine, send it out Ethernet card 4, I think it was. But if it's anything else, then send it out the other thing that goes out into the wall, right? And make it somebody else's routing at that. So that's the sort of decisions that the network layer would make on Legolas. Very simple. It's this one network do this, everything else goes someplace else. All right. So if it does have the address, though, again, it could figure out whether the host it wants is really on that network. So if we get something coming into Legolas and the host we want is 10 dot something or other, it knows that, hey, I can just send this back on this same piece of wire and get it directly where we want to go. I'm almost there, essentially. It might be a one-off transmission. And Frodo and Sam talking to each other, essentially, they would do that all within one hop. Okay, but if we have to go through other networks, we do, and this is the part that gets you to the next closest place towards your ultimate destination. So if we do pass something to Legolas, because we don't get it on our .10 network from one of your local machines, Legolas then decides what to do next, and almost always it's going to send that .254 address onto our local backbone, which then decides what to do with it next. Now these tables are dynamic tables. They change with time. If you get a lot of traffic on one place that you could go to, maybe you have an alternate route that you could send things to. Or some things go down, we can send things in a different direction. It's probably useful to look at this picture again for that. As I say, probably Cox has several different places it could go. One main connection, one perhaps backup connection to work with if something doesn't work. And similarly, these guys here are probably connected to each other and can also talk to each of these machines once you get in their local network. So this is probably not just one guy here, but a miniaturized version of what we've seen there or there. And up here on the back end, if it turns out that something goes wrong with that, then this guy has to decide, okay, should I go around that way to get to that host, or should I send it off this way to make it go there? It'll make these changes on the fly, essentially, as things happen, like your bumps fall or whatever. Okay. All right, so the IP stage is going to put another header on this. And then later the Ethernet stage is going to put yet another one on. So it's sort of like taking your message, putting it in an envelope, and the next guy down the line puts it in a bigger envelope and puts new addresses on it, and then the next guy, the Ethernet stage, puts it in an even bigger envelope with its own idea of addresses on it. And so that's what we're going to see happens here as we put things together and pull it back apart again. All right, so once it figures out which way to go with this, then it's going to put a new header on this thing, and that's going to be the IP header. So the important things in here, there aren't all that many fields in this particular header. But mostly it's the address of the host, the one who's about to do the transmission, where this message is coming from. And that's not necessarily where the message started. And where it's supposed to go to, where the next hop is, which probably is not Rohan, but somewhere along the way to Rohan. Right, so we have different starting and ending headers here than we had in the previous pattern. We can find its ultimate destination by opening up this envelope and peeking at where it really is supposed to go, but that isn't going to happen until we move this packet along to the next machine. The next guy is going to have to peek at that and figure it out. Right? But all we're trying to do is figure out how to get to the next spot. All right. So, you're somewhere on the internet coming from home here. It's gone a ways here. Maybe you've gotten to this one, the front door of SJSU.edu. That's an internet address that you're trying to send it to, not an Ethernet address. So IP doesn't get to deliver this thing here. It just figures out what the internet address is and where you want to go, and then hands it off to the next layer. And that's the link layer. That's the guy that needs to figure out how I'm going to put this on the wire, whatever my network is right now, to get it to the next most reasonable place. So this thing wrapped already into two different envelopes here is sent down to the link layer. And now this is the guy who's going to put the Ethernet address on there, something that can be understood by the hardware that we've got. Remember, Ethernet addresses are 6 octets, whereas internet addresses nowadays are still just 4 octets. The version 6 thing are coming along with it, also making those guys a lot bigger too. All right. All right, so the link layer can peek into the IP header here, because It hasn't put its own header on. Yeah, figure out where this thing is supposed to go, and that's not, again, the ultimate destination, but just the next hop along the way. Right, so we can figure out what that is. Now we'll try to look up. We may already know what the Ethernet address is that corresponds to that internet address. Right, or it might not. It might not be in its ARC table. There's this address resolution protocol that figures this stuff out. Okay, so first time it tries to do this, a new address I hadn't heard of before, right, then we wouldn't be able to just find that lookup already in the table. In that case, you broadcast an ARC request to everybody on your local address, and you hope that you're going to get a response which says where it is. There could be a machine that says, hey, that's me, just send it to me. Or it could be that you have your router says, okay, I'm responsible for doing things that are going in that direction, so send it to me. But we'll figure out what the answer is, the Ethernet address is supposed to be used for the next hop. And then it remembers that for a while. Doesn't remember it forever, by the way, because we can move things around. Right? A laptop could get unplugged from a given network here and move to a different wireless network or whatever. So we don't want these answers to be set in stone forever. Stuff you have in the ARC cache here stays there for a while, but after 10 hours or so, it makes the machine go and look it up again to see if things have changed. And you as an administrator, if you are moving equipment around, you know you really are changing things here. Typically you flush the ARC cap at the ARC tables here. Just clear out all its memory of everything here because you want it to look up this new place where this new machine is that you just moved it to. And let it start all over again with a bunch of queries, and now it will find where the new place is. Otherwise, hours will go by where you don't seem to be able to talk to this machine and you just unexpectedly move to a different network. And so as an administrator, that's something you may have to do as you're moving machines around on your network. Fine, but one way or the other is going to get an answer of what to do with this packet, who to actually send it to over the physical layer that we're talking about. In this case, it's in the Ethernet that these guys are connected to. So now we don't want an internet address on there. We want to put an Ethernet address in a new envelope, essentially, around the stuff that we've got. So we won't erase the internet addresses that we've already built up. We put a new envelope around it with the internet address of where it's going to, and of course your own address, so that it applies, the acknowledgments or whatever can come back. Right, and we also add a little something on the very end of this thing to give us a checksum. So that was also in this picture too. When we put in that Ethernet header, we do put some stuff in the front, and we've got 32 bits of error correcting code down here. So even if it gets slightly garbled, this guy can figure out where the mistakes were and flip those particular bits. If it gets really garbled, then you don't have enough information here to reconstruct it. You just have to ask for it again. But small discrepancies you can generally just fix on your own because of the error correcting code that's back here. It's especially important for things like wireless networks when sunspots are acting up and things like that. Radio transmissions are not as reliable as sometimes in the year and under some conditions. Alright, so we add some stuff to the front, add some stuff to the back, and now you've got something that we can really send out on the media. So again, we wait until no one else is talking on the actual wire, and then we send these bits down. And again, everybody hears this stuff. Everyone is going to look at the first few bytes that came from this address. And those guys would be this stuff. And in particular, they care about, hey, is the address of where it's going to meet? Or is the address where it's going to a broadcast address? So it'll pay attention to either of those. And if in those first few bytes it doesn't find the information it expects to have there, it knows it's not a message that it hasn't paid any attention to, and it just throws that guy away. It's not going to put it on its incoming stack because, unless you're in promiscuous mode, because it's not intended for this particular machine. All right. So every host hears this message. Generally, only one of them, broadcast is actually going to respond to it. So if they say, hey, that's me, then it can take this guy and pass it up to the next highest level. Well, it'll do the checksums to make sure they've got something that makes sense, so that address is legal. But if it is, then it'll pass it up to the next layer, back up to the network layer. All right. So when we go back up there, that guy is going to peel off the outer envelope and figure out the remaining humps. Right? It's going to discover, oh, it came to this guy here. Am I this guy, or do I need to send it along to someplace else? So discovers, okay, this guy was headed for me, but that doesn't mean it was the final destination. We have to pull off that header and look at where it's really going to. And it wasn't just the front door of SDSU, it was really Rohan that we were headed for. So now we go through part of that process all over again. We have peeled back a few of the envelopes that we put around this thing. Here we have an Ethernet address that we could look up, peel that back, realized, okay, this is going to us, 130.191.1, right? And then we peel that back to find out where it's really supposed to go to, which turned out to be Rohan. And so now we're going to send it back down the line here. We have to prepare this thing. We have to look in our router tables of this new machine, the front door of sdsu.edu, to say, hey, where do you go to get to Rohan? And the answer presumably would come back as 130.191.3.254, right? The router for the .3 subnet at SDSU. The Rohan was 3.100. So all the 3 dot guys should go to this router if you're not already on that subnet. So next we want to send it along to that spot. So we construct a new IP header here to say, hey, I'm coming from the 1.1 guy, and I'm sending it to the 3.254 guy. So we'll make an IP header, and then once we have that, we send it down the line to the link layer. And the Ethernet header then says, hey, which one of your interfaces from 1.1 do I need to go out of to get to 3.254? And it'll put the appropriate Ethernet address on here again to send it to this guy. And then it puts it on the wire as soon as there's some flag on the wire. And it should then arrive at this guy. We'll check it for errors, same song all over again. We'll check it for error, peel back the headers here, try to find out where it's really supposed to go to, and we'll discover it's Rohan. Right? The final address is 130.191.3.100. And because of the net masks that we talked about last time, we'll say, hey, my network matches the network of the destination. I don't need any more intermediaries. I should be able to figure out how to deliver this thing right away. So again, we'll build up with an IP address that looks exactly like this, and then the Ethernet header will send you to whatever the Ethernet card. Actually, it's a fiber optics card. Let's not get into that. That would get it to where it needs to go. Okay. So that, with all that build-up, that should help you figure out a little bit more about how these things work and interact with each other. Payload, which we wrap up into more and more envelopes. And we keep peeling off the outermost envelope, looking at where it needs to go next, and bundling it up to get to the next spot. Right, so that's what's being described in this OS thing. So eventually, when we get it to really the Rohan, we can pass it all the way up the line back to the SSH daemon that's listening on port 22. And then the SSH daemon prepares a response. You may recall in that innermost layer, we said where this thing came from, what port number, on your home machine, and whatever your address was to get to your home machine. And that then will prepare a response to go to that address at that port number and claim that it's coming from Rohan, the 130.191.3.100. But it won't say the port number to continue the conversation on is 22 anymore. It will say, hey, I'm setting up something, a copy of the SSH daemon that's going to listen on port, I don't know, let's say 1, 2, 3, 4. And that's where you should continue the conversation. So I think we had seen earlier in the notes, if you follow what's happening here, if you look at your shell here, you have TCSH running, right? And you log on to Rohan or Eris, and you can see who his parent is. And it's one of those, a clone of the SSH daemon, essentially, as you've been talking to SSH. And we'll be listening on a particular port number. Nobody else is talking on that particular port. We've got 65,000 ports on the machine. So we can be doing holding lots of conversations at the same time without running out of port. It's a very big part. All right. Well, let's see. Somebody else just popped in my mind here as I was doing this. Yes. We talked a little bit last time about network address translation, the idea of masquerading. So things can get more complicated. Like for example, if we were trying to talk to Rohan from Sam or Frodo or Aragorn or something, we have our own idea of what our address is, and it's 10 dot something or other, which doesn't make any sense to the outside world. That's a private local network. So in order to be able to have something like this happen, where if I had 10 dot whatever being given to Rohan, it would have no idea how to get it back to us. We saw that Legolas takes care of those issues for us. When we want to send things out, we've been told to send stuff to Legolas. Legolas realizes we have this network here, and it's going to rewrite those packets here. Even though you want it to go back to 10.0.0.5, Legolas is going to take your packet and say, hey, send it to 130.191, 227.58. Send it back to me, Legolas. That's something Rohan knows about. And we'll tell it, hey, send it to port 7890 or something like that. We'll give it a unique port to come back on, and then Legolas remembers, hey, stuff coming onto this port really belongs to Aragorn at port number 3578 or whatever it is. So it fakes these addresses, and things appear to be talking to Legolas. As far as Rohan knows, it's talking to Legolas. But then Legolas, when stuff comes to this stuff here, it translates it and sends it down to your particular host. So that's how we can have fake addresses, coming from some place the rest of the world doesn't know about, and still actually be able to communicate in both directions with them. Legolas handles that for us by pretending that the stuff is supposed to come back to Legolas. And then when it gets to Legolas, it figures out, oh, I went to this port, I'm not really supposed to look at it here on this machine. I'm supposed to send it to one of my flock of sheep that I'm tending. Right, so there's many, many more complications about how all this stuff works, and hopefully that gives you a bit of an idea for what we're supposed to do. It's probably a pretty good stopping place for today. There is some more stuff that we haven't looked at in the textbook here that I still do want to cover. We haven't talked about how we do these lookups here. If you say rohan.sdsu.edu, how in the world do you get back this particular number that gives us the internet address? What we talked about here depended on having numbers like this that we could work with. We have to see where those things come from, even when you're doing a human readable name. And next time I may also bring in an old lab from Susie where we set up mail handling and things like that. We didn't get a chance to do that in the 9 labs that we did this semester, and I was reluctant to add a 10th one. But since we do have a little bit of time at the end of the semester, we'll talk about how you would configure mail. So that's what I hope to have happen next time. Okay, so we can quit a few minutes early today. Any last questions before we